12 spacecraft saw it. None of them were pointed at it. Their detectors went blind in the same second. Instruments built to measure the violence of the universe were overwhelmed by it. The light had been traveling for 50,000 years. On December 27, 2004, a wave of gamma rays crossed the orbit of the Earth. It lasted 0.2 of a second. For those 0.2 of a second, a dead star on the far side of the Milky Way was brighter in gamma rays than the full moon. Then it was over. The detectors recovered. The reports went out around the world. And 10 minutes later, something else arrived. A second signal. Fainter, slower. It climbed to a peak around 600 seconds after the first spike, and then it faded away over the next few hours. 3 separate instruments, built by 3 separate teams, recorded the same thing. Nobody could explain it. It sat in the archive for 20 years. Either the star's magnetic field was doing something no model had ever described, or something solid had been torn off its surface and was still burning as it flew. 2 doors. There is no third one. Kevin Hurley had spent his career at the Space Sciences Laboratory at the University of California, Berkeley, running the network of spacecraft that catches gamma-ray bursts. In April 2005, he and his collaborators published what those instruments had recorded in the journal Nature. The number is hard to hold in your head. In 0.2 of a second, that star released as much energy as the Sun radiates in 250,000 years. Not across its lifetime. In 0.2 of a second, the source already had a name, SGR 180620, a neutron star in the direction of Sagittarius, deep toward the center of our galaxy. It turns once every 7.5 seconds. It is about 20 kilometers across, the width of a mid-sized city, and it weighs more than the Sun. Its magnetic field is stronger than 1 million Gauss. The magnetic field of the Earth, the one that moves a compass needle, is about 0.5 Gauss. A hospital MRI scanner runs at 15,000. This object is a different category of thing, and here is the part that reached us. Umran Inan and his group at Stanford University measured what the flare did to the air above our heads. Their results appeared in Geophysical Research Letters in 2007. The gamma rays ionized the daytime lower atmosphere. Electron density at 60 kilometers of altitude rose by a factor of 100 to 1,000. The disturbance pushed down to about 20 kilometers, and the electrical conductivity it created lasted more than an hour. A dead star tens of thousands of light-years away changed the electrical properties of our sky. To understand why that sentence frightened people, you have to go back to 1992. That year, 2 theorists named Robert Duncan and Christopher Thompson published a paper arguing that a small fraction of newborn neutron stars should end up with magnetic fields 1,000 times stronger than anything then known. They gave the object a name, magnetar. For most of a decade, it was a word without a confirmed body attached to it. The observations came in slowly, and they came in through disasters. On March 5, 1979, a burst of gamma rays swept the solar system and staggered 9 separate spacecraft, including the 2 Soviet Venera probes that were descending toward Venus at that moment. Their radiation counters were reading a steady background of about 100 counts per second. In a fraction of a millisecond, the reading passed 200,000, and the instruments stopped being able to count at all. That source was not even in our galaxy. It sat in a supernova remnant in the Large Magellanic Cloud, more than 160,000 light-years out. It blinded hardware anyway. On August 27, 1998, a second event arrived, this one from a magnetar called SGR 1900+14. It did something a star is not supposed to be able to do. It changed the ionization of the Earth's night sky enough to be measured from the ground, by radio receivers, in the dark, in the middle of the night. 2 flares in 19 years, both from objects nobody had a full theory for. There is a reason 12 spacecraft happened to be watching at all. Hurley helped build something called the Interplanetary Network, and the idea behind it is almost crude. Gamma rays cannot be focused the way visible light can, which means a detector cannot point. It can only notice. The network answers that by scattering detectors across the solar system on probes headed for other planets, and when a burst sweeps through, each one is struck at a slightly different moment. Compare the arrival times, and the delays between them draw the direction the light came from. It is triangulation, the same method a surveyor uses. The baseline is hundreds of millions of kilometers wide. Then came December 2004, the third one, and the third was roughly 100 times more powerful than the other two combined. Think about the timeline hidden inside that. The light that saturated those detectors left its star before the last ice age ended. It crossed the plane of the galaxy while every human being alive was a hunter-gatherer. It moved through the dust of the Sagittarius arm while Egypt was being built, while Rome rose and fell, while the entire written history of our species was assembled out of nothing. And it arrived on an ordinary Monday, at spacecraft that had been in orbit for a handful of years, built by a species that had known the word magnetar for 12. The timing is close to absurd. Miss that window by a century in either direction, and there is no instrument on Earth capable of recording what happened. There is no second chance at an event like this. Giant flares of that size arrive roughly once a generation, and the last two hit a civilization that could measure them only crudely. We were ready by a margin measured in decades, against a signal measured in tens of thousands of years, which makes what happened next harder to forgive. The second signal, the slow one, the one that peaked 10 minutes late, was seen by 3 instruments. The first catch is the strangest of the 3. Europe's Integral Observatory carries a thick shell of crystal around its main telescope, called an anti-coincidence shield. Its entire purpose is to notice radiation coming from the wrong direction and tell the spacecraft to throw that data away. It is a filter. It exists to reject. Sandro Merighetti and his colleagues reported in 2005 that the filter had caught the glow. The CONUS detector aboard the WIND spacecraft caught it as well, and Dmitry Fredericks and his team published that in 2007. RESI, a NASA observatory built to stare at the Sun and never intended to look at neutron stars, caught it too. Stephen Boggs and his colleagues published that same year. 3 teams, 3 instruments. One curve, they described it accurately. They plotted it, they measured its energy, they put it in the literature, and then they moved on, because none of them had a mechanism that fit it. This is worth sitting with for a moment, because it is not a story about failure. Those groups did their work correctly. The signal was real, the measurement was sound, and the explanation for it had not been invented yet. There is a particular kind of scientific object that lives in that state, fully documented, completely visible, unreadable. The curve went into the archive. It stayed there while the people who recorded it moved on to other problems. It stayed there through the discovery of gravitational waves. It stayed there through 2 full rebuilds of the standard picture of how stars die. It stayed there while an entire generation of graduate students was born into the field, trained, and handed instruments and codes their predecessors never had. There is a version of this story where that never happens. Archives are enormous, and the incentive structure of science does not reward reopening a 20-year-old measurement that somebody else already published correctly. Old data gets cited. It rarely gets reread, but in 2024, one of them opened the file. Before we get to what he found, there is a second problem with this star, and it is a problem about a number. Every figure quoted up to this point rests on one assumption: how far away SGR 1806-20 actually is. The 2005 papers used 15 kiloparsecs, roughly 50,000 light-years. That is the number that produced the headline energy. That is the number behind the comparison with the Sun. The magnetar does not sit alone out there. It is embedded in a young, dense cluster of enormous stars, and for years the distance to the whole system was pinned by one of its neighbors, a monstrous variable star that some astronomers had ranked among the most luminous objects in the galaxy. In 2008, a group led by Joanne Bibby at the University of Central Lancashire went back to that cluster with the Gemini telescope and took near-infrared spectra of its brightest members: hot blue supergiants, Wolf-Rayet stars, the shedding, dying giants that mark the youngest clusters in the sky. From those spectra they measured a distance directly. They got 8.7 kiloparsecs, about 28,000 light-years, not 50, 28. Energy falls off with the square of distance, which means the correction is not cosmetic. Cutting the distance nearly in half cuts the calculated energy of the flare by a factor of about 3. The most extreme event ever recorded from outside our solar system had its defining number revised down by 2/3, 4 years after the fact. And it is still the most extreme event ever recorded from outside our solar system. A separate team came at the distance from a completely different direction a few years later. By timing the X-ray echoes the flare left as it lit up sheets of interstellar dust between us and the star, like a camera flash bouncing off fog. Their answer landed in the same neighborhood. That is the shape of this entire field. The object sits far enough outside human experience that the error bars on our measurements are wider than most of the phenomena we study. The revision did something else too. Hurley and his co-authors had already noticed that a flare this bright, if it went off in another galaxy, would look from here almost exactly like a short gamma-ray burst. Same duration, similar spectrum, which raised an uncomfortable possibility. Some fraction of the short bursts in our catalogues might not be distant collisions at all. They might be magnetars in nearby galaxies, misfiled. In 2020, astronomers confirmed one in a galaxy called NGC 253, 11 million light-years away. A burst that had been sitting in the records as a gamma-ray burst was a magnetar flare. Now, the second signal. To understand why it matters, you have to know about a much older argument, one that has been running since the 1950s. It is the question of where the heavy elements come from. Hydrogen and helium came out of the Big Bang. Carbon, oxygen, iron, those get built inside stars, and ordinary stellar fusion accounts for them cleanly. But fusion stops at iron. Everything past it, everything heavier, has to be assembled by a different route, by cramming neutrons onto a nucleus faster than that nucleus can fall apart. Physicists call it the rapid neutron capture process, the R process. Gold is made that way, platinum, uranium, the heavy elements in a phone, in a wedding ring, in the fuel rods of a nuclear plant. For 70 years, nobody could point at the place it happens. 3 candidates competed, and all 3 had real support behind them. The first is a collision between 2 neutron stars. In August 2017, gravitational wave detectors caught exactly that, an event now called GW170817, and telescopes around the world watched the glowing debris cloud for weeks afterward. The spectra showed freshly minted heavy elements cooling in the wreckage. That was proof. It was the first proof anyone had ever seen, and it looked, for a while, like the end of the argument. But it created a timing problem, and the timing problem never went away. Neutron-star mergers take a long time to happen. 2 massive stars have to be born as a pair. Both have to explode without tearing the pair apart. Both remnants have to survive the kick those explosions deliver. And then the 2 dead stars have to spiral inward toward each other for hundreds of millions of years before they finally touch. That clock is slow. It is slow in a way that matters, because when astronomers look at the oldest stars in our galaxy, the metal-poor ones that formed when the Milky Way was barely assembled, they find heavy elements already sitting in the spectra. Something was making gold before mergers had time to make any. It helps to know what the process actually demands, because the demand is brutal. To build a nucleus of gold from a seed of iron, you have to force roughly 100 extra neutrons onto it, and you have to do it faster than the nucleus can decay in between. That means a free neutron density beyond anything a normal star can produce, sustained for about a second, in matter that is already too dense to be called gas. There are only a handful of places in the universe where that condition can even be written down, let alone met. The second candidate is a rare kind of stellar collapse. A massive star spinning fast enough and magnetized strongly enough that its explosion flings neutron-rich material outward instead of swallowing it into the black hole forming at the center. Those are fast, which fixes the timing. The problem is that nobody has ever caught one in the act. Their existence rests on simulations rather than on a photograph. It also has to happen somewhere the finished product can escape. Build gold in the core of a star, and it stays there until the star dies and swallows it. The R process needs a violent exit as much as it needs the neutrons. The third candidate was, for most of that argument, not taken seriously at all. In late 2023, a theorist named Jakub Cichula at Charles University in Prague was working with Todd Thompson at Ohio State University and Brian Metzger at Columbia University on a narrow question about magnetar flares. Their paper appeared in monthly notices of the Royal Astronomical Society in 2024. Their argument was mechanical and almost domestic in its simplicity. A magnetar's crust is a solid, not metaphorically. It is a crystalline lattice of neutron-rich nuclei, packed to a density where a piece the size of a sugar cube would weigh about as much as a mountain range, and it is held under enormous strain by the magnetic field threaded through it. The field wants to move, the crust will not let it. The stress builds for years, sometimes for centuries. When the field finally reconfigures, the crust does not simply glow, it fails, it cracks, and the shock that runs through it drives a piece of that crust off the star at more than 1/10 of the speed of light. Neutron-rich material, blown into open space. At those velocities and those densities, the conditions for rapid neutron capture are met. The star does not only emit energy, it manufactures matter. That prediction had a testable consequence, and it was an elegant one. Freshly built heavy nuclei are radioactive. As they decay, they release a dense forest of gamma-ray lines, each at its own precise energy. And because the debris carrying them is moving at 1/10 of light speed, those lines get Doppler smeared into one another until they blur into something that is no longer a set of lines at all, but a smooth glow peaking near 1 million electron volts. The theory said that glow should rise over several minutes and then decay over hours. Anirudh Patel was a doctoral candidate at Columbia University. He worked out what the decay curve should look like in detail, ran the nucleosynthesis calculations, and then went looking for a magnetar flare bright enough to test it against. There was only one candidate in the entire record, December 27, 2004. He pulled the 20-year-old data. The curve matched. Predicted peak, about 1,000 seconds after the spike. Observed peak, between 600 and 800. Same shape, same fluence, same slow fade over the following hours. There is a detail in the arithmetic that is easy to walk past. The delayed glow carried a tiny fraction of the energy of the initial spike, a rounding error against the main flash. The spike was the star screaming. The glow was the debris quietly cooling behind it. Everyone had been reading the scream. The signal nobody could read had been a photograph of gold being made. Patel, Metzger, Cichula, Eric Burns at Louisiana State University, Jared Goldberg at the Flatiron Institute, and Todd Thompson published the result in the Astrophysical Journal Letters on April 29, 2025. And they did the work of trying to kill their own result first, which is the part that makes it worth believing. Could the glow have come from the star's own magnetosphere, from particles scattering resonantly in that monstrous field? Andrei Beloborodov had modeled that process in 2013. Run the numbers and it fails in two independent ways. It predicts a brightness 3 to 4 orders of magnitude below what was actually observed, and it should pulse in step with the star's 7.5-second rotation, because the field rotates with the star. The observed glow does not pulse. Could it have been the sun, some ordinary solar flare that happened to fire during the same window and contaminate the measurement? They pulled the X-ray record from the GOES weather satellites and checked. The odds of a coincidence like that are about 5 in 10 million. What was left standing was the crust of a dead star, burning. Here is the mass they calculated. In that half-second, SGR 180620 threw off and transmuted roughly 1/3 of the mass of the Earth in heavy elements. Gold and platinum are a fraction of that total, not the whole of it. Hold the comparison anyway. Every gram of gold humanity has pulled out of the ground in its entire history. Every coin, every ring, every bar in every vault on this planet comes to about 220,700 tons. One star, half a second. The accounting is not close. Scaled across the galaxy, the team estimated that magnetar giant flares could account for somewhere between 1 and 10% of every heavy element in the Milky Way. Which brings us back to the fear. The figure that gets quoted is real, and it has a source. In February 2005, the Harvard-Smithsonian Center for Astrophysics stated that a giant flare of this size, detonating within 10 light-years of the Earth, would destroy much of the ozone layer and drive extinctions. Now put the rest of that sentence beside it, the part that rarely gets repeated. There is no magnetar within 10 light-years of the Earth. There is no magnetar within 1,000. The closest one known, XTE J1810197, sits about 8,000 light-years away, and astronomers using the Parkes radio telescope in Australia were still tracking its behavior as recently as 2024. It is roughly 800 times farther out than the line where the danger is supposed to begin. Around 30 magnetars are known. Every one of them is thousands of light-years away, and the flare that blinded a fleet of spacecraft in 2004 reached us as a disturbance in the upper atmosphere that instruments had to be pointed at to find. Nobody felt it, nobody lost power, no satellite failed. The record does not support the extinction reading. What the record supports is stranger and harder to sit with, which leaves the harder question, the one that does not come with a threat attached. The gold in a wedding ring was in the ground before the ground existed. It was in the cloud of dust and gas that collapsed into the sun and the planets, and it got into that cloud because something violent enough to make it had happened nearby, earlier, and thrown it out. For 70 years, the honest answer to what that something was has been a shrug. It is now a short list, and one of the entries on that list has been photographed. We were never the target, we are the residue. Picture the file. Not the star, not the flare, the file. A curve in a data set, sitting on a server, correct in every measurement and meaningless for 2 decades, while the people who recorded it grew older and the field moved past them. Everything needed to read it was already there. What was missing was a sentence nobody had written yet. NASA is building an instrument called COSI, the Compton Spectrometer and Imager, led by John Thompson at the University of California, Berkeley, and scheduled to launch in 2027. It is designed to resolve individual decay lines instead of a blur. If another magnetar flares while COSI is watching, we will not be inferring the recipe from a smeared glow. We will be reading it, element by element as it is written. I have gone back and forth on how to hold this, and I have not settled it. The same kind of event that could strip the sky off a planet is the reason there is anything on a planet heavy enough to be worth mining. Those are not 2 separate facts about the universe. They are one fact, seen from 2 distances. The star was never the threat, it was the furnace. The last 3 generations of astronomers got one clean look at an event like this between them, and they came close to never reading it at all. The next one could arrive tonight, or in 80 years, and the only thing anyone can do about that is keep something pointed outward and keep the archive open. And somewhere out there right now, a crust is under a strain that has been building for centuries, and the next photograph is already on its way. Thanks for watching, and I'll see you in the next one.